Welcome to the Deep Dive. Today we're tackling something really central to modern tech, what we're calling the Great Data Paradox. It's kind of the essential roadblock defining where AI goes next. You know, for years we've heard this phrase, data is the new oil, right? It's positioned as this essential fuel for, well, everything exciting, precision medicine, new financial models, optimizing global supply chains, you name it. Progress seems to rely completely on getting access to huge amounts of high-quality, real-world information.
And that's absolutely the first side of the coin. That's the paradox. Because the other side is that this fuel, this asset everyone needs, is also a massive liability. Companies, researchers, they're incredibly data hungry, but with strict privacy rules popping up everywhere, I think GDPR in Europe, HIPAA for health data in the US.
Right.
And just the constant fear of data breaches, all that really valuable, sensitive, real-world data, it ends up locked down, stuck in these digital silos.
Yeah, the friction there is, well, it's intense. You can imagine, say, a big pharma company. They want to work with an AI lab on discovering new drugs. They might have millions of patient records, treatment outcomes, incredibly valuable stuff, but they absolutely cannot just hand over that real protected health information. It's just not possible.
Or think about a bank. Maybe they want to get better at spotting money laundering. They've got transaction data from, 3 different branches, but pooling that sensitive customer data spending habits, investments, it's just too risky, sometimes even within the same company. So the data stays stuck. It really does create an innovation bottleneck.
So, okay, that sets up the problem. How do we break that logjam? How can we build these smarter, more powerful AI systems that tackle big real-world problems, but do it while actually increasing privacy and lowering that breach risk?
And that right there is where synthetic data comes into the picture. It's this elegant and mathematically quite powerful solution to this exact paradox. It lets us get the statistical value, the useful patterns, the intelligence out of sensitive data, but without ever having to hold or expose the original risky information.
Okay, so our mission today is really to unpack that. Let's get past this idea that synthetic data is just, fake data. We need to understand the engineering behind it, how we can actually build better, safer data, basically from scratch.
Sounds good.
Let's start right at the core definition then. When we say synthetic data, what exactly are we talking about?
Okay, simply put, synthetic data isn't collected from a real person or a real event in the world. It's data that's been manufactured, it's generated computationally, often using quite advanced machine learning models, actually. And the whole point is to mimic the statistical properties, the patterns, the really complex relationships you'd find in a real original data set.
Right. And what's super important here, I think, is the distinction. Because people hear data privacy solution, and they often jump to something like anonymization. But this is fundamentally different, isn't it?
Oh, absolutely. That distinction is crucial. Anonymization. What that means is you take the real data, the actual records, and you try to scrub out the obvious identifiers. Black out the names, addresses, social security numbers, that sort of thing. But the underlying structure, the core information in that record, it's still the original data.
And we've seen again and again that approach, well, it often doesn't hold up under scrutiny. That scrubbed real data still carries a huge risk of de-anonymization. If someone knows just a few external facts about you, maybe your age range, general location, a specific medical procedure, they can often cross-reference that against a supposedly anonymized public data set, and boom, they've found you. The original data itself remains the weak point.
Exactly. Anonymized data is really just altered real data. You're kind of hoping no one can piece it back together. Synthetic data, on the other hand, is entirely new. It's generated. There are no original individual records to try and reverse engineer.
We sometimes use this analogy, the digital chef analogy. I think it helps make the difference really clear for people.
Ah, yes, the chef.
So imagine your sensitive, real data set is like a world-famous cake baked from a secret recipe. Anonymization, then, is like taking that exact cake, scraping off the icing where it says someone's name, maybe roughing up the edges a bit, and just hoping nobody recognizes the unique structure, the specific ingredients, the overall signature of that original cake.
It's still the original cake, fundamentally. Vulnerable.
Right. But synthetic data generation, that's totally different. The data scientist acts like a master chef. They don't even touch the original cake. Instead, they study its recipe very, very carefully. They figure out the proportions, flour to sugar, the statistical distributions, how all the ingredients interact in complex ways. They learn its statistical fingerprint.
And then they go to a completely new grocery store, Buy brand new ingredients, nothing carried over from the original cake, and they bake a brand new cake. It tastes, looks, feels statistically identical. It captures the essence of the original, but it contains absolutely none of the original molecules. That new cake is the synthetic data.
And that fundamental difference, that's really the #1 reason, economically and from a regulatory standpoint, why we're seeing such rapid adoption. Because this new data isn't tied to any real person or event, regulators generally agree it's not personal data anymore, not under rules like GDPR or California's CCPA.
Which instantly de-risks the whole data operation. Suddenly, this brand new synthetic data set. It can be shared more freely, you can sell it, use it in public coding challenges, run it on cloud platforms with far fewer headaches compared to the original source data. It basically solves that isolation problem we talked about.
And think about how practical this gets for developers. It solves the cold start problem completely. Say you're launching a new app, maybe a payment app. Usually you'd need months of real user transactions just to test your fraud detection models properly.
Right, you need data to build the thing that needs the data.
Exactly. With synthetic data, you can generate millions of realistic, statistically sound transactions, including weird edge cases, before you even have your first real customer.
And that democratizes access too, which I think is a huge accelerator for society. Historically, if you wanted to tackle really complex problems like analyzing medical images or doing detailed demographic modeling, you needed special access. You had to get inside the private data vaults of a big hospital or maybe a government agency. It was a privileged position.
But now, a small startup or an academic team anywhere, they can potentially work with high-fidelity synthetic versions of that protected data. It means innovation can happen much more broadly without needing that kind of insider access to the really sensitive systems.
And beyond just access, it helps deal with the inherent messiness and limitations of real-world data. Think about that fraud detection example again. In reality, like 99.9% of transactions are totally normal. This huge imbalance where the thing you actually care about, the fraud, is super rare, makes it incredibly hard to train a good AI model.
Yeah, you can't just copy the few fraud examples you have over and over. The model just learns to spot the duplicates, not the real underlying patterns of fraud. But with good synthetic data generation, you can create millions of new, realistic, but importantly, distinct examples of fraudulent transactions. You can create a perfectly balanced data set for training.
Exactly. We can effectively fill in the gaps where real data is sparse or just, well, imperfect.
Okay, so how do we actually get this high degree of realism, this fidelity, as you call it? You mentioned advanced models earlier.
Right. The key is often using sophisticated generative models. Things like generative adversarial networks, or GANs, are very common.
GANs. Okay, these can get pretty complex, but maybe we can give a quick idea. For our listeners, the basic concept is you have two neural networks kind of fighting each other.
That's a good way to put it. You have a generator network. Think of it as the data forger trying its best to create synthetic data. And then you have a discriminator network, that's the data detective, trying to tell if the data it's seeing is from the original real data set or if it's a forgery from the generator.
And they go back and forth?
Constantly. The generator keeps getting better at making fakes, and the discriminator keeps getting better at spotting them. This whole competitive training loop pushes the generator until its synthetic output is so statistically realistic that the discriminator basically can't tell the difference anymore. That's why the final synthetic data can be so statistically accurate. It's had to pass this incredibly tough test.
Okay, this sounds, it sounds almost like magic, which usually means we need a reality check.
It's complex engineering, right? And that always comes with trade-offs. If the data is so realistic it fools the detective network, how do we actually guarantee privacy? Isn't there a risk there?
You've absolutely hit the nail on the head. That is the central engineering challenge. When data scientists are building these synthetic data systems, they're constantly managing what we call the synthetic data trilemma. It's like one of those triangles where you can push towards one corner, but you move away from the others. You can't perfectly maximize all three things at once.
Okay, so what are the 3 points of this trilemma, this impossible triangle?
They are utility, fidelity, and privacy.
Utility, fidelity, privacy. Got it. Let's break those down. Utility.
Utility is basically asking, how useful is this synthetic data in practice? If you train your AI model, say your fraud detector, on the synthetic data, does it actually work well when you finally deploy it on real-world data? We often measure this by looking at things like predictive accuracy. Does it make good predictions? Makes sense. Then fidelity.
Fidelity is about statistical similarity. How closely does the synthetic data mirror the original real data? in terms of its statistics? Does it capture all the subtle correlations between different columns? Does it replicate the rare patterns, the distributions? If the fidelity is low, your utility is probably going to suffer too. The model won't learn the right things.
Okay. And the third point, privacy.
And privacy asks, how safe is this new synthetic data from attacks trying to learn about the original data? Specifically, the big concern is something called a membership inference attack. This is where a sophisticated attacker tries to figure out, just by looking at the synthetic data, whether a specific person's real record was used in the original dataset that trained the generator model.
Okay, wait. So if the whole point of the Jan training was to make the synthetic data look statistically identical to the real data, doesn't maximizing that fidelity automatically make it easier to infer things about the original? Doesn't high fidelity inherently put privacy at risk?
That is precisely the tension. And it's why just running a standard Jan isn't enough for privacy-sensitive cases. Specialized engineering is needed. The solution often involves intentionally building in a layer of mathematical protection during the generation process. And this is where a concept called differential privacy usually comes in.
Differential privacy, or DP. Okay, that's another term you hear thrown around a lot. How can we explain that simply for someone who hasn't, worked directly with this kind of cryptographically protected data?
Let's try an analogy again. Think of differential privacy as a way to mathematically inject a carefully controlled amount of noise or randomness into the process of learning from the real data and generating the synthetic data. This noise is calibrated, it's not just random static, it's enough to subtly blur the statistical contribution of any single individual in the original dataset.
Okay, so it fuzzes things just enough.
Exactly. It ensures that if you generated synthetic data using dataset A, which includes, say, Jane Doe's record, versus dataset B, which is identical but excludes Jane Doe, the resulting synthetic datasets would be statistically indistinguishable. An attacker, looking at the output, couldn't tell whether Jane was in the original training set or not. The overall trends, the aggregate statistics are preserved, which maintains utility, but the individual's presence is masked.
So you're essentially adding just enough statistical fog to guarantee that even a really powerful adversary can't definitively prove if my specific record was part of the original pool used for training.
That's the core idea. And that brings us right back to the trade-off and the trilemma. To get a very high, mathematically provable guarantee of privacy using differential privacy, you generally need to increase the amount of noise you inject.
Right.
But the more noise you add, the more you inevitably start to slightly distort some of those fine-grained statistical patterns and correlations from the original data, which means you typically sacrifice a bit of fidelity and consequently maybe a bit of utility.
So the real engineering skill is finding that sweet spot, dialing in the right amount of noise for the specific job.
Precisely. It becomes about finding the optimal setting for the specific use case. If I'm generating synthetic medical data, maybe for training an AI to read x-rays, patient confidentiality is absolutely paramount. So I might accept slightly lower utility, maybe the AI is 90% accurate instead of 92%, in exchange for that rock-solid differentially private guarantee.
Whereas if I'm just creating synthetic weather data for, a public climate change model, individual privacy isn't really the concern there.
Exactly. In that case, the risk is basically zero. So you tune the generation process to maximize fidelity and utility, maybe using a little or no differential privacy, because privacy just isn't the constraint for that particular problem. The choice always comes down to the required risk tolerance in the specific application.
Okay, so wrapping this up, what does this all mean for you, our listener? I think the big takeaway is that synthetic data isn't just fake data, not at all. It's a really sophisticated, mathematically engineered solution to this huge data access versus privacy dilemma that's honestly been slowing down innovation globally.
Yeah, it really is unlocking new possibilities. Entire new fields of research are opening up. It's helping protect individual privacy much more robustly, certainly on a larger scale. And it's fundamentally changing how companies think about data governance, especially in regulated sectors like banking and healthcare. Leading organizations are already using this today. They're using it responsibly to build the next generation of AI systems.
It feels like the era where groundbreaking innovation required exposing sensitive personal information might actually be starting to end.
I think that's right. And maybe the final thought to leave people with is this. The future of data isn't just about getting more and more big data anymore. It's increasingly about smart, safe, and yes, synthetic data. That really feels like the key to keeping up the pace in this age of AI.